So let me start. Probably we will have 3 videos today because I have a first video of the first part of the lesson, a second video by me in this small second part by me, and finally we should have a third video by Francesco Sartari. Okay, let me do this last part of my lesson here. Close your microphone, please. Okay, and let me share with you. I've shared, yes. And go back here. Now we want to focus this part. What about this term? This term is a loading vector, but this loading vector is loading in the discretized world. Is a loading vector in the discretized world. I have to transform my physical vector in the real world in this loading vector. What about my physical load? I have a body, a generic body like this. Excuse me for my draw. It's very generic, and I have surface force like this. Force per unit surface per unit surface, and this force field is T. Note that this is very important in elasticity because this unit surface vector is represented essentially by the aerodynamic force for a wing, so very important. And so we have surface force, physical force. This is a physical vector, note, 3 components for each surface point. You have a vector, and you have also another color. You have force like rho F force. This F is a force per unit mass, and so the product is a force per unit volume. And this force, for example, is the gravity. So this green here is a force, physical force per unit the unit volume. Okay, and this is defined in each internal point of the body. So here we have internal body, and here you have surface on the surface body. Okay, now what about work W that this kind of force are able to perform for a generic displacement vector? So if you assume the work performed by T and rho F corresponding to a generic displacement delta U, we can call this work W delta. And so W delta, delta W, not W delta, delta W. Delta W is, by definition, you have to take the integral on the volume of rho F dot delta U and integrate, please. The same on the surface, integral on the surface of the surface external force T per unit surface dot delta U. in the S. And that's all. Okay? This is physical. This is the physical point of view. You are a vector field of force, external force, performing a work on the elastic body. What about the U? But U is the displacement expressed like psi m qn. So a generic, or if you prefer arbitrary displacement delta U is given by the combination of the same shape function by an arbitrary set of Q known as delta Qn. Okay, so the delta function is expressing the genericity of the displacement you can obtain. Okay, the arbitrarily of this displacement, and to a displacement arbitrary correspond a set of arbitrary Lagrange variables. Then substitute inside, and you have that delta U, the job, is equal to the integral rho f dot summation of psi m delta qm. Okay, dv plus integral of t dot summation of psi m delta qm ds. Okay, again, the delta q quantity are not dependent on time, and therefore you have that you can write this work like the summation of quantity like rho, excuse me, let me write better this. And I am just finished. You have summation of integral of rho f dot psi m dv plus the integral of t dot psi m, and all this quantity is multiplied by delta qm. So in the new discretized world, you are stating that this work is equal to a combination of some generalized force depending on m, and this generalized force can be defined like em, and these forces are able to perform a job in an identical way. And you can evaluate this job, this work better, by multiplying this generalized force by the generalized corresponding coordinate. And therefore, that's the definition of EM. The EM is a vector of components like E1, E2, E13. Remember, what is it? 13247, 13247, the last one, and the generic of this is equal to the integral on the volume, the projection of your physical weight force, for example, but in general volume force, projected to the m shape function plus the projection of your surface force onto the nth shape function in the S. And this is the definition, the relationship between your physical load, this is a physical load, like this, like this and this. These are the two physical vector fields acting on the wing, and this is the discretized, the space discretized load. In order to write this, what this load is representing. Remember, what is psi? What is psi? Psi is the shape function. So if you have, just an example, if you have a distribution of pressure on your body, you have something like this. You have a pressure distribution. You have this. The green is the pressure field on this red wing. This is a red wing. So this is a physical quantity T. Imagine to have this shape function on the wing. This shape function. You have a shape function. Here you have a hat function, something like this, at this point. At this point is the degree of freedom 17. What about E17? E17 is equal, you don't have F, you have only T. So this is equal to integral of psi 17 dot T. Yes. What happens? Take your green pressure distribution, multiply by your shape function, and what you obtain? You obtain a force applied on the node 17. And this is the discretized load, guys. This is the meaning of the discretized load with respect to the physical load you have on your structures. Okay? I hope to have given to you a good idea of what is a linear scheme for representing a dynamic of a structure. And the dynamic of a structure is always represented by this equation. Not in the case of the beam or the plate. No. In general cases, we have this kind of equation. Okay? And we have clarified the role of this quantity, and this quantity. Okay? So I want to leave the ball to Francesco Sartari, and he will talk about the property of this matrix and a suitable eigenproblem to be associated with this problem for solving this equation. After this stage, now you want to solve this problem. And the solution aspect is an aspect related to an eigenproblem associated to the matrix N and K. So I want to leave the ball to Francesco, and see you tomorrow, everybody. Arrivederci. Certo. Ok.
Hi guys, do you hear me?
Yes.
Aspetta. Let me share.
Devi parlare molto forte
Okay,
perché
okay.
non ti sentono.
Okay. No, sorry, I was wrong. No, this is not the right whiteboard. Okay, perfect. Okay, so this part of the lesson we will learn how to solve. First we perform the eigenvalue problem of the system that Professor Mastrotti has just obtained, and then we will solve the free response of such a system. Okay, so let's start from the equations of motions of the space discretized structure. Do you see the whiteboard?
Yes.
Okay, perfect. Give me a feedback now if you read it there. Okay, so the equations of motion just written by the professor can be expressed in this way. And no, and multiplied by q dot dot plus k multiplied by q. This is equal to e.
Troppo leggero il tratto,
Okay, let me do another problem. Okay, let me do attempt to solve this issue. Okay. Start with yours. Okay, now it's better. Okay, so the questions are m expressed in the nodal coordinates multiplied by q dot dot plus k, that is the mass stiffness matrix expressed on the nodal degrees of freedom, multiplied by q. This is equal to to E expressed in nodal coordinates. Of course, now, in order to solve the problem, in particular today we are interested in solve the free response of this structure, we need to transform this equation. So this equation can be transformed by performing the eigenvalue problem. In particular, we are interested in solve this problem. So we have k multiplied by an eigenvector zn that is equal to the eigenvalue lambda n multiplied by n multiplied by zn. Okay, these provide two objects. These objects are the. Sorry guys, I have to get confident with this instrument, this tool. These objects are the eigenvalues lambda n that are equal to the ratio between zeta n transposed, that is our eigenvector, is one of the n eigenvector that we can get by solving the eigenvalue problem, multiplied by k, k is multiplied by zeta n, or divided by zeta n transposed by n zeta n. Okay. As you know from the class of threshold dynamics, this must always be greater than 0. Okay, or at least equal. For instance, when we consider rigid body motion, and so rigid body modes. Okay, and then we obtain also the eigenvectors, zeta n, for instance, such that we can express, if we pre and post multiply this eigenvector to the mass matrix or the stiffness matrix, we get, I write it directly in a vector form, we have that if we take into account an eigenvector zeta p and an eigenvector zeta s, and we apply these two eigenvectors that are different eigenvectors, so that can be different at least. We pre-multiply the mass matrix by this object by zs, we get that zeta p transport m post multiplied by zeta s, this is equal to m p multiplied by delta ts. This means that these eigenvectors are able, these eigenvectors are able to diagonalize our mass matrix, and in particular we will have a mass matrix that is everywhere null except on the diagonal, where we have a non-null term is equal to mp when p is equal to s. So, and then we also have that zeta p multiplied by k multiplied by zeta zs is equal to kp multiplied ps. And also in this case we apply the same concept. Okay, so in a matrix form we can state that the capital zeta, that means that is a matrix obtained by collecting all of these eigenvectors. So we have zeta z1 and so on up to zeta zn. The previous relationships can be rewritten such as z transpose m post multiplied by capital Z is equal to a matrix, that is the modal mass matrix, and similarly that transpose multiplied by k.
Francesco, excuse me. Excuse me, Francesco. It's just a check. Are everybody sharing in a white screen the Francesco whiteboard? In this because I can't.
Okay.
Francesco?
Yes.
Check, please.
Okay, perfect. Sorry, guys. Okay, maybe in the record the first part of the presentation is missing now. Okay, and this is equal to the modal stiffness M. Okay. Now,
I can see Francesco. I don't know the other.
Prof?
I don't know the other guys. Please check.
The other guys said earlier that they can see the whiteboard.
Okay. Okay.
Okay. But I forgot to start the recording of the registration of the session, but I did just a few,
Okay.
provide some concepts. Okay. So now this is the eigenvalue problem where we obtain the eigenvectors and that have the capability to diagonalize the system, and in particular the ability to diagonalize the mass and stiffness matrices and the eigenvalues. Eigenvalues lambda e and lambda n that are equal for a structural system equal to omega n squared, that are the natural frequencies of the system. Okay. Okay. Now we can express the set of Lagrangian coordinates that we considered that consists of the displacement, the nodal displacement, the displacement of the nodes, the degrees of freedom of the nodes of the space discretized structure. This displacement vector can be expressed as modal superimposition of the eigenvectors, sum of n, of eigenvectors Zn multiplied by the modal coordinates Qn. Okay? This means that we can consider this Q as the sum of zeta 1 multiplied by Q1 plus zeta 2 multiplied by Q2 plus and so on. Okay. This can eventually be recast in this way by means of the matrix of eigenvectors multiplied by Q, modal Q. Okay? Since these eigenvectors have the property to diagonalize the system, the mass matrix, and the stiffness matrix, we can state that rewriting all the equations for the space discretized structure written in terms of nodal degrees of freedom, we can say that m q dot dot plus k q is equal to E, but since Q hat is equal to Z, capital Z by but Q, we can write M by Z Q bar dot dot plus K multiplied by Z Q equal to E hat. Okay. Now, if we pre-multiplied all of this by z transpose, we get the modal mass in here, the modal stiffness in here, and this object, this object represents the set of external modal forces. That are the forces, the set of forces that are obtained when projecting the external forces, external load onto the vibration, the gain vectors. Okay? No. Okay. Now, okay. Okay. Sorry. Okay. Now, what about the gain modes of the system? So basically, at the beginning, so you are used to write. Okay. Okay. You can just know that we can express the displacement of each point of the structure as the superimposition of a set of Morse shapes Cn multiplied by Qn that represents the set of nodal degrees of freedom. Okay. Now we want to express another set of modes Morse shapes that are not the shape functions associated to the nodal displacement, for instance the time function, but represents the Morse shapes of the system. So basically we define a vector, a modal, a displacement field that represents this mode as Cn, in this case, no, not the case. I don't know what happened, but okay. We represent Cn, where C are the modes, as the sum of n C Cm, where this Cm hat is the adjoint function, multiplied by Z Mn, dove Z Mn are the current value of the eigenvectors for be selected for the n degree of freedom. This is that, where n is the radix that corresponds to the n Morse shape. Okay. And then, finally, we can express the modal mass and stiffness matrix. We can express the modal mass and stiffness matrix in this case by projecting, for instance, the density and the structural operator directly on the Morse shapes of the structure. So, for instance, we could also, earlier, basically, we obtain the modal mass and stiffness directly by solving an eigenvalue problem. Okay, now we would like to obtain the model mass and stiffness by projecting the Mohs shapes on the structural operator. So, for instance, we can obtain that M at S, model M at S. So we would like to obtain the component at S of the model matrix, model mass matrix. We can obtain this component by projecting on the by means of the integral in the volume of the density by the Mohs shape CR scalar CS in the B. Okay, but since this relationship is valid, we can also say that this is equal to, this is also equal to the sum on two indices that are E and J, for instance. Okay, of the integral on the volume of the Z. Okay, let me check again. Okay, C. 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 E by Z E R scalar C. Okay, of course this is C J R S in the component J. Okay, in the D. I'm trying to get used to this kind of white also. Okay. Now, okay. So basically, this can be expressed just in this way: sum on Ej of Z E R by the integral of rho C E C J in the V, first multiplied by the J of the S. Okay. Of course, we can recognize in this the model, the mass matrix, the nodal mass matrix Ej. So finally, we can express. We can express this system such as Z transposed multiplied by M Z transposed R multiplied by M, sorry, okay, Z, I think that's again, okay, Z R by M nodals was multiplied by Zs. As earlier, this is equal to delta Rs by mr. Okay? Of course, this procedure can be repeated for the case of modal stiffness. So we can obtain the modal stiffness K KRS, sorry, as the integral on the volume of water of sum on 2 for sum km c r e comma j plus c j comma e of r c composed outside the integral e j k m by c s k m plus c s m k in the B. Okay, if we apply the same procedure as for the mass matrix, we will end up to get that KRS is equal, as earlier, to ZL transpose multiplied by the stiffness matrix expressed in order division freedom, plus multiplied by theta s. That is equal to KR, by delta Rs. Okay, so we were able to get the mass matrix, the modal mass matrix, and the modal stiffness matrix by means of two different procedures. The first by solving the eigenvalue problem, and then in a parallel way we were able to obtain these two matrices by projecting once the density by applying the definition that the component of the mass matrix can be obtained by projecting the density on the model shapes, and similarly we got the components of the modal stiffness matrices in the same way. Actually, it was forecasted today to get to the free response of the structure, but we don't have time. So I think that the class is over. Okay, finish. Goodbye.